to the prince of all topics, organic chemistry. So in this topic, we're going to look at, for the SL component, the fundamentals of organic chemistry, which is the focus of the lesson today, functional group chemistry, and then for higher level, types of organic reactions, synthetic routes, and stereoisomerism. So by the end of this topic, or unit, you should have an idea of what a homologous series is, what structural isomers are, what structural formulas are, what functional groups are, what saturated compounds are, and in particular the unsaturated compound benzene, which is quite important to organic chemistry. And you should all be able to explain the trends of boiling points in a homologous series, identify the different classes of organic compounds, identify therefore the typical functional groups of these particular classes of compounds, construct 3D models of organic molecules, and apply the IUPAC rules to the nomenclature of straight chain and branched chain isomers, and identify primary, secondary carbon atoms. And finally, be able to discuss the structure of benzene using physical and chemical evidence. Right. So, what is organic chemistry? Well, let's have a little video to explain.
Guten Tag. I'm Friedrich Volar. I know you've probably never heard of me, but I've never heard of you either, so that makes us even. But there are a great number of scientists who recognize me for my work with urea. Do you even know what urea is? Well, kind of sounds like urine, right? That's because it's a related compound. In fact, it's the main nitrogen-containing substance in pee. Yeah, that's right. I said pee-pee. Well, actually, I only said pee the first time, but now I just said pee-pee. So why all this talk about pee? Well, because before I came along and synthesized urea in the lab in 1828, the whole world thought that there was something fundamentally different between the chemistry of living things and the chemistry of non-living things. In fact, we even had a name for the compounds that made up organisms. We call them organic compounds. We assumed that because organic compounds could only be found in forms of life, they existed as a result of some vital force that was unique to living things. But when I, much to my surprise, accidentally made urea in the laboratory, I proved everyone wrong, including myself. So as a result of my work, we now know there is nothing particularly unique about the so-called organic compounds, as they behave just like the compounds found in non-living things. Today, we consider organic compounds to be anything that contains the element carbon. And to think it all began with P. Weird, huh?
So, in order to understand the concepts around organic chemistry, we need to use certain terms. Okay? And these are the terms that you need to know, for SL at least. The first one is hydrocarbon, which contain hydrogen and carbon. Makes sense. Homologous series, compounds with the same general formula, which we're going to go through. The molecular formula, which shows the number of atoms only. The structural formula, showing how the atoms are arranged in 2 dimensions. And the empirical formula, which shows the lowest whole number ratio of atoms. So here is an example. Okay, we're looking at the alkanes, which you're familiar with from last year. So the homologous series is CnH2n plus 2, the general formula, which you can basically determine if the particular compound falls within that series. The molecular formula is C4H10 for this particular example, known as butane. And the structural formula here is how it is arranged in 2 dimensions, where of course the sticks represent bonds between atoms. And we have the condensed structural, CH3, CH2, CH2, CH3, so we just kind of remove the sticks. And the empirical formula, the simplest ratio, which is going to be dividing each side by 5, so C2H5. So a homologous series is the general trend for all molecules in an homologous series is an increase in the boiling point. Okay, so no matter what homologous series, be it alkanes, alkenes, alkynes, or alcohols, usually what happens is the more carbons you add, the more the boiling point is going to increase. This is because of earlier work, which we looked at structure and bonding of the London Dispersion Forces and the molecular weights of the lengthening carbon chains. So you can see here that one carbon of an alkane has a boiling point of about minus 150. When you add 2, there are more intermolecular interactions, and that's minus 100. Propane will boil at about minus 50-ish, and butane at about 0, and finally pentane, it's now becoming positive. It's going to actually be a liquid. Then we have structural isomers. So structural isomers have the same molecular formula but different structures. So here's 2 examples here. We have a straight chain isomer of butane, okay, known as N-butane. So the N just means that it's a straight chain. And then we have a branched butane molecule, okay, what's basically a propane molecule. We'll go into the naming later, but it still has 4 carbons, but now it's branched, so it's a structural isomer. So in organic chemistry, we use the concept of functional groups. So functional groups are atoms or groups of atoms attached to a hydrocarbon. They're usually the reaction or reactive groups, things that undergo in reactions, and they're on a stable carbon chain, so form an important part of the molecule. And examples that we're going to look at are the alcohols, the aldehydes, ketones, carboxylic acids, and the halides, which are the halogen alkanes. So basically an alkane where a hydrogen is replaced with a halogen. The first family, I guess, or homologous series we're going to look at is the alkanes. So they're all called alkanes. They have a general formula of CN2N plus 2. Okay, the functional group is called the alkyl, and well, the functional group name is called the alkyl groups, and they have no functional group in a sense because they're just single bonds, and the suffix is -ane. So if you have a hydrocarbon which just has carbon and hydrogen, and they're all single bonds, that's going to be an alkane. There's an examples there, and this is how we name them. Okay, so if you have one carbon, they have the meth prefix, okay, for example, methane. If you have 2 carbons, the eth prefix, okay, they have 3 carbons, the prop prefix, it's 4 carbons, but prefix, and 5 carbons, it will be the pent prefix, and 6 carbons, the hex prefix. Okay, so you could make up stories about that, so make acronyms. So my elephant poops bananas profusely and hereditarily or something. Okay, just make a little story to help you remember those prefixes. And then they're all anes because, for example, CH4, if you draw out the structural formula with bonds, they're all going to have single bonds to carbon. Okay, and alkyl groups are branches on carbon chains. So a CH3 group, again with all single bonds, is known as a methyl group. So if you've got 2 carbons, it's going to be an ethyl group, again all single bonds, and propyl group, butyl group, etc. Okay, you're just following the same prefixes as the previous slide, but you're now putting -il at the end. Okay, so being chemistry, there's always rules, and in order to name alkanes, we use the IUPAC naming summary. Okay, IUPAC, the International Union of Physical and Applied Chemistry. Okay, it's kind of the international body of chemistry which makes the rules in terms of naming. So everyone's naming compounds the same way. So the first thing is you count the number of carbons in the longest chain. Then you name each attached group. And then you count the longest carbon chain to give the first attached group the smallest number. And then name and locate each group. Okay, so here's an example here. Here is a compound, okay? So you're going to go, well, the longest chain is going to be 1, 2, 3, 4, 5, 6, okay? So that's going to give your hexane. Then you've got a methyl branch, okay? That's a CH3 group. And then it's on the 3rd carbon, so we'll call it 3-methyl hexane. There's an example there. So the next homologous series is known as the alkenes. They now have a general formula of CnH2n, and the functional group name is the alkenyl. And the functional group now is that we do actually now have a functional group. It is a double bond. Okay, so if you see a double bond, chances are it's going to be an alkene. Okay, and the suffix is now not ane, but ene. So just like before, the prefixes are the same, F, prop, but, pent, and hex for the number of carbons. But now instead of ane, you've got ene. Okay, the number of carbons, ethene, if you have 2 carbons, and the structural condensed former is going to be CH2, CH2 this time. Okay, remembering general formula is CHN2N. So when naming branched alkanes, okay, with the alkene component added in, you select the longest chain of carbon atoms containing the double bond and name the chain from this end. Place the ending "ene" on the basic name and then use a number to indicate the lowest number carbon from the carbon-carbon double bond. As in alkanes, prefix with substituents, and then the side chain positions are based on the number allocated to the first carbon in the carbon. So if we look at this example here, it's going to be, what's the longest carbon? You've got chain, okay, you've got 1, 2, 3, let's do the correct numbering. You've got 1, 2, 3, 4, 5, 6, okay, because that's going to be the chain, like that, CH3. Okay, so it's going to be hexene, something. Okay, it's the double bond is going, the smallest number is going to be on the second carbon, so it's hex2ene. So then we go 1, 2, 3, 4, 5. The CH3 is on the 5th carbon, so it's 5 methyl, because it's a CH3 group, hex2ene. So you can also have structural isomerism in alkenes, just as you had with alkanes. And the reason for this is you have different positions in the double bond. So here we have 1, 2, 3, 4, 5 carbons, but you'll notice that the double bond, the lowest number, is now on the first carbon. Well, here it is on the second carbon. So that's pent1ene, whereas that's pent2ene. And you can also have branching. So there's 1, 2, 3, 4 carbons. Okay, the lowest number for the double bond is the carbon number 1. Okay, so it's going to be but1ene, because 4 carbons is the but prefix. And on the third carbon, you have a methyl group. So it's 3-methyl-but-1ene. The next homologous series is going to be now the alkynes. Okay, the class name is the alkynes. The formula is now CnH2n minus 2. And the functional group is the alkynyl group. And now instead of a double bond, we've got a triple bond. And the suffix is now -ine, Y-N-E. So the alkynes, again, the same prefix. Okay, 2 carbons. It's going to be eth, 3 carbons prop, etc., etc. But now you have the -ine suffix, and the condensed structural formula is going to be now CH if you have 2 carbons. Obviously, you cannot have methine because there's no carbon or triple bond to bond with. And basically, this discusses the concept now of saturated and unsaturated hydrocarbons. A saturated hydrocarbon are hydrocarbons that contain no double or triple bonds, so the alkanes, and unsaturated hydrocarbons are the alkenes and the alkynes, okay, because they can now contain double or triple bonds. So now looking at a special class of the alkanes, the halogenalkanes, okay, so they have a formula CnH2n plus 1, and then we have an X. And mystery number X is the halogens, either fluorine, chlorine, bromine, or iodine. And the functional group is known as Rx. They don't have a suffix, just like the alkanes, but they have a prefix depending on what the halogen is. So if it's fluorine, there's going to be fluoroalkanes, alkanes, bromoalkanes, iodoalkanes if it's iodine, etc. Okay, so the halides and namings, different positions for the halogen and branching at the carbon chain. Okay, so again, we're listing the number of carbons, actually probably not that way, 1, 2, 3, 4, so the lowest number goes to the carbon which has the halogen attached. Okay, so it's 4 carbons, so it's going to be butane, because it's an alkane. It's going to be 1 chlorobutane because the chlorine is attached to the first carbon. Whereas here it is now the second carbon, so you then name it 2-chlorobutane as a structural isomer. So in terms of branched alkanes, the priority, the first word or the first prefix is the halogen. Okay, so it's going to be again the lowest number, which would be 2 in this case. The longest chain is 1, 2, 3, so that's why it's propane. You've got a methyl on there as well, so it's 2-methylpropane, and then it's 2-chloro-2-methylpropane, because also not only is the methyl group on the second carbon, but there is a chloro group. And you'll notice that the highest priority goes to the chloro group. Okay, so that's going to be 1-chloro-2-methylpropane in that second example. So the methyl group is on the second carbon and the chloro group is on the first carbon. So the number of carbons that are joined to the carbon with the halogen group determines if it's called a primary, a secondary, or a tertiary halide. So if you have only, so this is our first carbon attached to the halogen. So if the adjacent carbon, okay, if there is one adjacent carbon, then it's known as a primary haloalkane. If there are 2, okay, 1, oh, what am I doing? Crazy. If there is 1, 2, then it's known as a secondary, and if it's got 3, 1, 2, 3, it's known as a tertiary halogen, okay, haloalkane, okay. And also note that if you replace the carbon with a hydrogen, it's still a primary. So the next functional group is the alcohols. Okay, they have a general formula of ROH. Okay, so R can be any other group, alkyl, alkenal, alkynyl. They have a functional group name of hydroxyl, and it's going to be ROH, and the suffix is now ol. So just like alkanes, alkynes, and alkenes, basically the number of carbons determines what the prefix will be. Okay, so it will be 2 carbons will be F, okay, and the ane remains, but now you've got an ol. Okay, so it's ethanol. Now obviously there's only one place the OH group can go on in ethanol, so it just remains as ethanol or N-ethanol. Whereas here we have 2 structural isomers. Okay, they are structural isomers. Structural isomers, because the OH can go either on the first or second carbon. Again, you're prioritizing the ol group onto the lowest number. Okay, so this becomes, so it's not propan 3-ol, it'll be propan 1-ol. This is given the value of 1 in terms of naming. And it's 1, 2, 3 carbons in the longest chain, so it's propan, and it's propan 1-ol. Whereas here, this becomes on the second carbon, 1, 2, 3, so it needs to become propan 2-ol as structural isomers. And that can continue on if it's 4 carbons, the longest chain, butan 1-ol, okay, pentan 1-ol, and these are again the structural isomers associated with, well, pentanol and butanol. Okay. So the number of carbons that are joined to the carbon, just like in haloalkanes, determine whether it's a primary or secondary or tertiary alcohol. So it's a primary, so that can be either an H or a carbon. That's fine, that's primary, just like in the previous example with haloalkanes. If the carbon bonded to the OH has 2 carbons next to it, it's known as a secondary, and if it has 3 carbons next to it, it's known as a tertiary alcohol. 1, 2, 3, primary. The next functional group is the ethers. Okay, they have a general formula of R, O, R prime. Okay, R can equal R prime, or R can also not equal R prime. They can be different or the same, doesn't make a difference. Okay, as long as there's an oxygen in the middle there, then it's going to be ether. And the functional group is here. Okay, and R is any, again, alkane, alkyl group, or alkenyl group. And the prefix is in the middle of an oxy. So there's no suffix. Okay, so you won't know it's an ether from the suffix, but you'll know that the midfix, okay, in the name, which will be a reflection of what the 2 R groups are, is oxy. So what does this look like? Well, that's methoxymethane, okay, because you've got your CH3 groups here, okay, which are equivalent to CH4, so it will be methoxymethane. Whereas this here is 2-ethoxymethylpropane. Why do you say? Okay, so we've got 1, 2, 3 as your longest. Well, no, actually not your longest chain, is it? I am wrong. 1, 2, 3 as your longest chain. Okay. Then you've got the CH3CH2 group. So that's where your ethoxy comes in. So it's on the second carbon. Okay. Notice on the second carbon here. So it's going to be 2. And there's a methyl group attached to the second carbon. So it'll be methyl. And you've got the longest chain being a propane. So it'll be 2-ethoxy, 2-methylpropane. The next functional group is the aldehydes. Okay, RCHO is the general formula, named aldehydes, and this is the general functional group, what it looks like. Okay, so basically it's an R group plus a COH group. Okay, and the suffix is now L. So naming aldehydes, again, you've got 1, 2 carbons, so it'll be ethane, okay, because it's 2 carbons, and we put the L at the end. Okay, 1, 2, 3 carbons, so it's propanol, and so on and so forth. The next functional group is ketones, which are R, C, O, R prime. Again, R prime and R can be different or the same. The new functional group name is the carbonyl group. Okay, so it's R, C double bond O, that's the carbonyl. Okay, that's carbonyl, is that part there. Okay, and R and R prime can be the same, and the suffix, or different, and the suffix is -one. Okay, so here's some examples here. So again, we've got 1, 2, 3 carbons, so it must be propane, and -one at the end because you've got that carbonyl group popping up. And then we've got 1, 2, 3, 4 carbons, so it will be butanone, etc., etc. Now again, you can have structural isomers because it depends where the double bond of where the carbonyl, the carbon double bond, turns up. Okay, so the longest chain here is going to be 1, 2, 3, 4, 5, but you'll notice that the carbon with the carbonyl is the second carbon, okay, the smallest number again, so we have pentan 2-one, whereas in this example, even if we went back the other way, the carbon is on the double bond either way actually, so either 1, 2, 3 or 1, 2, 3, it won't make a difference. The carbon number 3 is the carbon with the carbonyl on it, so we have it as pentane 3-one. So the next is the esters. Okay, there's quite a number of them. So you would have probably looked at that not last year, but in IGCSE. So it's R, C, O, O, R prime. Again, R and R prime can be the same or different. The functional group is known as the ester, and the suffix is the O8. So in terms of naming esters, the first part is from the alcohol group of the parent alcohol that the ester has been made from, and the second part is from the acid of the parent carboxylic acid, and then you add an O8. Okay, so let's look at methyl ethanoate. Okay, so the first part here, the CH3O, is the methyl because it's come from methyl alcohol, methanol, and the second part of it is going to come from the ethanoate. Oop, it's a bit not very nice and pretty. Okay, the second part's going to come from the ethanoic acid. Okay, so structural diagram here. This part here comes from the primary alcohol. That's the methyl part, and then the ethanoate part is going to come from the acid. And it's 1, 2 carbons, so it's ethanoate. Conversely, ethyl ethanoate comes from ethanol. Okay, this part here, and methanoic acid, or formic acid as it's also known, comes from ants. Okay, but it's for IUPAC, it's methanoic acid. So the next, since we are discussing carboxylic acids now, the next functional group is the carboxylic acids. Okay, RCOOH. They have a carboxyl functional group just like the other one, but you've also got a OH group attached to that carboxyl group. So the suffix for those are oic acid. And carboxylic acids also form a homologous series. So again, if you've got one carbon, that will be meth. Okay, methanoic acid. Okay, 2 carbons, ethanoic acid or vinegar. You might more commonly know it as. Now you've got 3 carbons, so it'll be propanoic acid, etc., etc. So in terms of naming carboxylic acids, you select the longest chain of carbon atoms containing the COOH group, remove the E and add an oic acid after the basic name. So instead of you'd have propan, you'd remove the E and make it propanoic acid. And the chain starting with the N nearer to the COOH group. So this takes priority. As in alkanes, the prefix, you also have prefix with the alkyl substituents. Side chain positions are based on the carbon at COOH being 1. So the acid basically takes priority. So how did we name this guy here? Okay, well, we know we're going to start off at 1. So it'll be 1, 2, 3, 4, 5 carbons. And the CH3 group is going to be projecting out. Okay, so it'll be like that. So it's going to have 5 carbons, so you're looking at pentanoic acid. And on the 4th carbon, you've got the CH3 group, which of course is called a methyl. So it'll be 4-methyl pentanoic acid. The next functional group is the amines. Okay, they're RNH2, and they're amino, and the suffix is now an amine. Okay, quite common in foods, especially protein-based foods. The nomenclature is named after the group surrounding the nitrogen. Okay, so you've got 2 carbons, so you're going to go with ethyl amine. Okay, this one has 2 methyl groups, so it's dimethyl amine because it's CH3 methyl. This is trimethyl amine, a great base. I've used it much in my PhD. And this is known as phenylamine. Now you're probably unaware of this because the C6H5 is unclear to you, but that's going to be known as a phenyl group, also commonly called aniline. We then have the amides, nearly there. They're RCONH2, similar in a way to esters. The functional group name is now called the carboxamide. Okay, this functional group here, the NH2 connected to a carboxyl group, and the suffix is amide. And if you're naming amides, the solids are named from the corresponding acid. You just remove the oic and add an amide. So for example, if you didn't have CONH2 and you had instead COOH, OH, then it would be called ethanoic acid. But because you've got the CONH2 now, it's known as ethanamide because it's got 1, 2 carbons, ethanamide. And this is known as N-phenylpropanamide at the bottom because remember, we've discussed it already, C6H5, okay? And the reason, and that's the phenyl group, okay, which become more familiar with you, and you've got 1, 2, 3 carbons there, so it must be propanamide. Okay, and the N, what does the N mean? The N means that the substituent is on the nitrogen. Then we have the nitriles, RCN, functional group name is the cyano, RC triple bond N, suffix is a nitrile, and in terms of nitriles, you're just doing it normally. Okay, so you've got 1, 2, 3, 4 carbons, so it will be butan nitrile. Okay, so it's just like an alkane. Okay, you name it like an alkane, but instead now because you've got that carbon triple bond N, you call it a nitrile. And that's 1, 2 carbons, so it's going to be ethan nitrile. Then we have the arenes, which we just touched on. That's CnH2n-6. The functional group name is called the phenyl, and that's what it looks like. It looks a bit weird, okay? We're going to explain why it looks a bit weird soon. And it doesn't have any suffix. And the reason why that's why it looks weird, like a circle, is because you've got basically two resonance forms of the benzene molecule. So due to the resonance energy or stabilization energy of benzene, it is reluctant to undergo addition reactions, which we'll learn about later, but will also will undergo substitution reactions. Okay, and what's happened is that this kind of circle in the middle is an illustration of the two resonance forms. Okay, and that's called delocalization. And the reason why you have this delocalization is it minimizes the repulsion between electrons. Wonderful molecule. And the physical evidence for the stability of benzene, so if you look at the X-ray bond lengths, if it was completely alkane, it would be a single bond length will be 0.154 nanometers. If it was completely all double bonds, it would be 0.134 nanometers. However, if you look at the X-ray data for bond length of benzene molecules, it's actually somewhere in the middle, which suggests it's kind of got a 1.5 bond length. A hybridization between the single and double bonds. And in terms of naming arenes, arenes are compounds with a benzene ring to start off with. Aliphatics, so that's kind of a term we've not used to yet, but aliphatics are basically non-resonance kind of species. Okay, so that's your CH3, your alkanes, your alkenes, your alkynes. So basically things that haven't got benzene rings. So for arenes, they're called benzene. Okay, if it's standing by itself, and you're going to name it bromobenzene because it's got a bromine sticking on it. Okay, and obviously if you have two bromines, it'll be depending where it is. So this is okay, this is bromobenzene, but for example, if it was on there, you had two of them, then it would be 1,2-dibromobenzene, okay, and so forth. And that's what we illustrate here. So this is 1,2-diphenyl ethine, okay, so we've got ethine in the middle, okay, 1, 2, okay, there's 1, 2 phenyl groups. Okay, so it's going to be on the first and second carbon, so it must be 1,2-diphenyl ethine. So in terms of the physical characteristics of functional groups, it can be used to explain volatility between functional groups, okay, hydrogen bonding and van der Waals interactions, and also explains solubility. Okay, so ethanol tends to be soluble, okay, whereas propanol is slightly soluble. So you're increasing the carbon chain, it's going to reduce in solubility because you've got an increase in van der Waals interactions. And in terms of effects of lengthening the chain and branching, there's a wonderful FET that we're going to be using in class that's going to illustrate this point. Okay, so as you increase the chain length, the boiling point actually increases. Yep, because you've now got more interactions between the chain lengths, as you can see. So here we have only 2 carbons, here we have 4 carbons, that's minus 161, that's 36. And obviously if you have bulky groups, it's going to be kind of intermediate, okay, compared to this has got 4 carbons, this has also got 4 carbons. Because of the 3D interactions, that's going to form like more flat layers, so there'll be more interaction between the 2 carbon-carbon chains, whereas this is less likely to pack well, so it's only got a boiling point of 9.5 degrees Celsius. Okay, so that's quite a lot of stuff, I must admit, and that is your introduction to organic chemistry.